That sound is real. It is also not what most people think they heard. This is Cosmion. Point it at any question in the universe, and it will show you the answer, whether you can bear it or not. Tonight, we point it at a black hole and ask a very precise question. When NASA gives a black hole a voice, what exactly are we listening to? The answer changes 3 times. One sound moved through gas. One began as light. One crossed 1 billion light years by stretching space itself. They are all called black hole sounds. They are not the same kind of evidence. Start with a sound that should not exist. The first signal comes from the Perseus galaxy cluster, about 240 million light-years from Earth. Hundreds of galaxies live inside it, wrapped in an enormous atmosphere of hot X-ray gas. Most of the cluster's ordinary matter is spread through that atmosphere rather than locked inside the galaxies. That gas matters because sound needs something to travel through. At the center is a supermassive black hole. Material falling towards it powers jets that punch cavities into the surrounding gas. Each outburst pushes on that gas again. Chandra found the pressure from those outbursts traveling outwards as vast, repeating ripples. The pattern was so large and so slow that it took years of X-ray observations to make it visible. These are literal sound waves. The cluster contains enough gas to carry them, even though the emptier space between worlds cannot. But no human ear could hear the original note. It is just over 57 octaves below middle C, close to B flat. The image on screen is 550,000 light-years wide. One pressure cycle takes roughly 10 million years to cross its own wavelength. The gap between 2 pulses is longer than the entire history of our species. A loudspeaker cannot wait 10 million years for the next pulse, so the Chandra team compressed that impossible rhythm into human time. They raised signals by 57 and 58 octaves. That means multiplying the original frequencies by 144 quadrillion and 288 quadrillion. Before we explain anything else, listen to it properly. The pitch has been moved. The pressure pattern has not. The rises, falls, and rough edges come from structures measured in the gas around the black hole. Nothing there was recorded by a microphone, and no sound escaped from inside the event horizon. The activity around the black hole pushed on real matter. That matter carried a real wave. The strange part is what that wave may be doing. The Perseus cluster loses heat as its gas shines in X-rays. Left alone, much more of that gas should cool, fall towards the center, and form stars. Astronomers do not see enough cold gas to match that prediction. The black hole keeps disturbing it. Energy carried by jets, bubbles, and pressure waves may replace much of the heat the cluster loses. So the deepest note we have ever identified may help decide how quickly an entire galaxy cluster can grow. That was the honest sound wave. The next black hole never made a sound wave at all. This is M87, 55 million light-years away. Its central black hole has the mass of about 6.5 billion suns, and it launches a jet thousands of light-years into space. The sonification uses 3 views of that jet. Radio data sits at the bottom, visible light in the middle, and X-rays at the top. A scan moves from left to right. Brighter pixels become louder. Higher points in each image become higher notes. Radio becomes the lowest instrument. Optical light takes the middle. X-rays take the highest range. The image is being read as a score. Listen for the bright core first, then the broken climb of the jet. That sound did not travel through M87. It was built from light collected by telescopes. Every note still points back to a measured pixel, but the mapping was designed here on Earth. Your eyes see a bright core and a thin jet. Your ears catch gaps, clumps, and changes in intensity as time. The scan also keeps the three wavelengths apart, so the low, middle, and high instruments can be followed at once. The data has not changed. The route into your mind has. This is what sonification does well. It does not pretend space has air. It gives a second human sense access to the structure inside an image. And then there is the third sound. It began with no gas and no light at all. On the 14th of September 2015, two instruments in the United States moved by less than 1,000th of the diameter of a proton. The movement came from two black holes that had collided about 1.3 billion light-years away. One held about 36 suns. The other held 29. They circled faster, drew closer, and turned their missing mass into a wave in spacetime. LIGO was built to catch that wave. Each detector has two vacuum arms, 4 kilometers long, set at right angles. A laser is split down both arms, reflected from mirrors, then recombined. If the arms stay equal, the light cancels. A gravitational wave disturbs that balance. As the wave passed, space stretched one direction and squeezed the other. The change was smaller than a proton by 3 orders of magnitude, yet both detectors found the same pattern. The signal reached Livingston first. Roughly 7 milliseconds later, it reached Hanford. That tiny delay helped prove the disturbance had crossed Earth. On the plot, the two traces carry the same unlikely shape. The black holes orbit faster. The frequency climbs, the amplitude grows. Then both lines end in a final burst. Random ground motion does not arrive at two distant detectors with that same rising fingerprint. Scientists call that shape a chirp. Here is the original listening version, at the measured gravitational wave frequencies. That is it. A fraction of a second. Almost polite. The event was anything but small. About 3 times the mass of our Sun vanished from the final black hole and left as gravitational wave energy. At its peak, the merger produced more power than all the stars in the observable universe combined. The new black hole kept vibrating after the collision, shedding the last distortion until it settled. That fading signal is called ringdown. There is no solid surface inside it to ring. The shape of spacetime itself is relaxing. It is the closest a black hole comes to behaving like a struck bell. LIGO's published animation plays the measured frequencies, then shifts them higher so the change is easier to hear. Listen to the climb this time. LIGO did not hear air moving. It measured distance changing. Turning that waveform into speaker motion lets our ears follow the shape of spacetime for one brief moment. 3 sounds, 3 different physical claims. Perseus gives us pressure waves moving through hot gas. M87 gives us light mapped into pitch and loudness. GW15V0914 gives us a measured ripple in space-time mapped to a speaker. Calling all three the sound of a black hole is convenient. Knowing the difference makes each one more remarkable. There was no microphone floating beside an event horizon. There did not need to be. The universe changed matter, light and distance, and our instruments kept the evidence. Human hearing covers a narrow strip of reality. Science extends it, not by inventing a voice, but by translating measurements we would otherwise never sense. Listen to Perseus once more. This time, hear the hot gas, hear the scale, hear one pressure cycle taking longer than our species has existed. A black hole does not need a voice to change its surroundings. Sometimes the evidence is a ripple 500,000 light-years wide, waiting for someone to turn it into a note. The lens does not blink. Subscribe, because next time we point it at the dead stars that spin hundreds of times each second and sweep the dark with beams precise enough to keep time.